Oh, I might list the name in IUPAC, or I might list some common names for the substituents. So it could be either or. But if I give you a structure, you can you can name it however you want with the common names, or with the IUPAC way of naming the branch substituents. Okay? So either or, but if you're given a name, I'm not saying you will, if you're given a name, you have to draw something, you should be aware that it might appear with the common names too.
Can we review some of the common names?
Sure. What is... Actually, let me just do it on there. All right. All right, so say my R here. Sorry, I don't know why I did that. So R is just the rest of the molecule. Okay, so say I have it branched like this. All right, what's this group called? Right there. Yep, so the common name, isopropyl. Okay. Now if you have the R group listed through here, CH, CH3, CH2, CH3. All right, do you know the common name of this one? No, it's not isobutyl. Sec-butyl. So look at this carbon. It's secondary. Secondary carbon. Sec-butyl. All right. If we compare this to this group right here, so CH2, CH, CH3, CH3. All right, what's this one called? Yep, isobutyl. So isobutyl is the one that looks like isopropyl, except it has one more carbon atom before you get to the branching point, and then it's 4 carbons, so that's isobutyl right here. You see 1, 2, 3, 4 carbons, so it's a butyl group, and it's the one of the isomers of butane, with the branch group there. So that's why it's isobutyl, because it looks like this part looks like, if you look at this part, right, it looks like this part right there. Okay? All right, there's one more for 4. Anyone know? Terbutyl, right. So R, that's our attachment. C, CH3, CH3, and then CH3. So that's terbutyl. So be aware of these groups as well, because you might see in chemical structures things abbreviated like this. So you may see things like this, TBU. All right. So we don't want to draw all that out. We could just write this substituent here as TBU on some chemical structures. So that's why we should know what this looks like, T-terbutyl. All right. And this would look like IBU. And then there's really no abbreviation for this one, but isopropyl would be IPR. Or sorry, it won't be uppercase. It'll be IPR, like that. Isopropyl. All right. For example, if I have a group like this, and I have an oxygen atom, but I don't want to draw out the rest of the carbon atoms, I could simply write this. OIPR. So that means there's a isopropyl group attached to this oxygen here. But don't worry, this is just FYI, okay? Oh, sorry, there's not that carbon right there, okay? That's just how that's how we kind of communicate structures. In Chem sometimes, we just use these abbreviations too.
Professor?
Yes.
Can you do neopentyl?
Yes. Neopentyl is CH2, and then I believe CH3. All right. So, terbital group with an extra CH2, that's neopentyl. Okay. So those are the common names that you could use for nomenclature, okay? And then the IUPAC names, those are how we systematically name them, okay? Just how we've been doing, naming the chains in nomenclature. For the complex substituents, you want to number those chains, and then you can name them systematically too, okay? All right, so those are our common names. Okay, so those are the most common ones you'll see. I think I did get them all. So, yeah, 1, 2, 3, 4, 5. Yeah. If I missed, and I don't think I missed any, but. All right, any other questions? No? All right. So, like I said, for radical halogenation, what you should be able to do is, if I give you an alkane, you should tell me how many different possible mono coordination products there should be. Okay? Don't worry about the mechanism. Don't worry about which one is the major product. Okay? We haven't really talked enough about that yet. And plus, I probably will just plan to test this probably on the next quiz. Okay? So not today. All right, but are there any questions about monocoordination? Any questions about the rates or the relative reactivity? Does that make sense? So they systematically, I won't say dumbed it down, but figured out exactly how well this reaction behaves. So they got it down that these type of hydrogens react in a certain way, these other types of hydrogens react in a certain way, and the last type of hydrogen, tertiary, how they react in a certain way. And they don't all react the same, so it's not based on statistics, it's actually based on reactivity of the intermediate, which is the radical that I talked about, okay? So we'll kind of clarify, go more detail on that today, okay? So, I think we left off after coordination. So now we're going to talk about fluorination. So instead of chlorine, fluorination uses what? What halogen instead? Fluorine, yes. So fluorine, we'll figure out here that it has terrible selectivity. All right. So fluorine, we all know about fluorine, right? It's electronegative, not very happy by itself. So as a radical, it is not very picky here. It will try to bond with whatever hydrogen atom it can find. Okay. So let's look here. H3C. All right, H. So we have two different H's here. We have a lot of methyl H's. And then we have fluorine. Okay? All right, so two products can form. All right, what's one of them? One of them is where the chlorine is, sorry, not the chlorine, the fluorine is going to be on the central carbon, the tertiary position. So this is the tertiary position. All right, now where would the other product, what would the other product be if we just have monofluorination, just one fluorine substituting? Oh, okay, well, we would get hydrofluoric acid. What's the other like alkane product we would get? So it would appear on one of these methyl groups, right? So CH2F. All right. So we have, remember like last time, a statistical or expected ratio, and then our experimental ratio. Okay, so let's write that, our statistical. In parentheses, expected ratio. All right, so we expect that out of all these hydrogens, which there are 10 in our starting alkane, only one of them is in the center. So that's 10% out of 1 out of 10, or 10%. And then we have 9 on the methyl groups. So we should see 90% of the second product, the primary fluoroalkane, and then 10% of the tertiary fluoroalkane. Okay. But what do we see in an experiment? So an experiment is actually quite opposite. We do see a ratio that's close to 1 to 10, 1 to 9, or sorry, yeah, 1 to 9. Or 10 to 90%. It's 14 to 86%. So that's pretty close to what we expect. So here we could say fluorine doesn't care. It doesn't have a preference for which hydrogen we say abstract. And that's because if you go through a primary radical or a tertiary radical, fluorine doesn't care. The activation energies are very low for either one. So they're not really in competition, okay? What drives it is that there's more methyl hydrogens available, so there's more possibilities to get one of those more often than say encountering the central hydrogen, which is just one in each molecule. Okay, so it's all based on like what's readily available, so statistics. So fluorine, terrible. You would never use this for synthesis because it's so reactive. You have no selectivity at all, which you kind of need in synthesis if you're trying to get to a target molecule. Okay, Captain?
Just to clarify what Jacob said, even though like the tertiary carbon is more stable, it would still choose the primary carbon because it's more available?
Yes. So the thing about fluorine radicals, they're not really stable by themselves. So they'll react with any radical that forms the fastest. And it turns out it doesn't matter if it's primary, tertiary, or secondary. Fluorine doesn't care. Fluorine will just react quickly enough with any of those radicals. So yeah, it has no preference, right? Good. So like, remember when we said the more methyl groups around a radical, more hyperconjugation? Well, that doesn't seem to play a role in fluorine because the fluorine radical is now super reactive. That will react with any radical intermediate that forms. Okay? Yeah, good point. Thank you. All right, any other questions? So remember fluorine here, terrible selectivity. If you see this reaction, you're going to be like, okay, what kind of hydrogens are there more available of? I'm going to write that product as the major product, okay? The more stable radical, the tertiary one, that one is so small because there's probably going to be less of those types of hydrogens, as we see in this example, 1 out of every 10. Okay. All right, so any questions about that? If we compare our rates to the chlorine example on your notes, you'll see that we saw the opposite, right? We kind of saw a more even balance, but not in this case. It's kind of what we expect based on, you know, the number of hydrogens available. All right. Now we come to the reaction that is synthetically useful for synthesis, so it's the most useful one, okay? All right, chlorine is useful if you can only form one product and it's secondary. That's pretty much what it's used for. But for targeted synthesis, bromine is actually the way to go, okay? So let's talk about bromination. So bromination is, this time we're using bromine, is very selective. All right, and that's because we'll see that the relative rates of bromine is very high. They're very large, okay? So let's do the same example. We have tert butane reacting with bromine, in our case. All right. All right. So I didn't write a temperature light for the other one, and I think it's because the fluorine is so reactive, it'll just go. Chlorine, bromine though, they need some help, okay? But fluorine so reactive that you probably could just add a little heat and it'll just go like that. Fluorine is reactive. All right, so let's just write the products again, but instead of fluorine, we're going to put bromine. So we have trimethyl, and then bromine right there, and then all right, CH2Br. All right. Well, this is very selective. Does anyone have a guess what the ratios are? Well, let's just say what the ratios should be, okay? Well, they should be, as we saw before, 10 to 90, right? We should say only 10% of the first product and 90% of the other product. But now let me ask you, what do you guys think the actual ratio is if it's very selective? The opposite. It's even more than that. So this is greater than 99%. And this is less than 1%. Okay, so bromine will always want to form on the tertiary carbon. So that's pretty selective. And if we need to get bromine there, this is the way to go. Okay, for what we know in our, kind of our organic kind of toolbox or tool set. All right, so let's try to explain this, okay? So bromine radicals, if we compare it to fluorine radicals, what do you think the reactivity is? Is fluorine more reactive, or is bromine more reactive? Fluorine, right? That's why it wasn't picky. Well, bromine is stable, so it will only target the most stable radical intermediate, okay? It can't form primary because primaries are hard. Primary radicals, very hard to form. But if you can form the tertiary radical, that is formed the fastest because it's the most stable, okay? So we could say here is that the carbon radical, this one, so we just listed it right here. All right, most stable forms the fastest. Okay, because it forms the fastest, our bromine's around. What do you think it's going to react with? This radical that forms the fastest, or the primary radical that forms the slowest? What do you guys think? So let's look at this radical here. So this radical, even though there's more positions for this kind of radical to form, right? Like this guy right here. Least stable. Forms the slowest. So what this means, it takes a lot of time to form, takes more time. All right? So if it takes more time, right, you're not going to see that as often because the tertiary radical here is quickest to form. That's the radical bromine we'll see, and it will react with it right away. Okay? So the case for fluorine, though, these radicals, it didn't matter which one formed because fluorine was so reactive that it will just abstract any hydrogen it can see. Okay, so that's the major difference. Fluorine's too reactive. Bromine is less reactive, so it will only react with the radical that can form the fastest. So the reactions are controlled by two different things, right? Fluorine is monitored or governed by the reactivity of fluorine radical or fluorine atom. And then bromine is so stable that it only will react with the carbon radical that forms the fastest. And that's the most stable one. And we saw before, carbon radicals of the tertiary, their bonds are weakest, the CH bond, so they form the fastest. And they're the most stable. Okay? All right. Are there any questions about that, Catherine?
So because chlorine is more electronegative than bromine, that means that chlorine is not as selective as bromine, but still chlorine's still more selective than chlorine.
Right. It's right in the middle. Mm-hmm. Good. All right. So now let me tell you the relative rates, because you would need to know the rates to kind of be able to predict stuff like this. Okay. So let's go over here. Relative reactivity of a H in monobromination. All right. So we have tertiary, secondary, and primary. All right, primary is always going to be 1. Secondary is 80 times as fast, but tertiary is 1,700 times as fast. So that is going to win out if you have a battle with primary, and most often, if you compare tertiary to secondary, that will also win out because it's almost, let's see, 1,700 divided by 80. Almost 100 times, I think, increase there. Or 10, maybe. No, almost 100. Okay? All right. So that explains why the product distribution here is so one-sided. Bromine, very selective. So that's very useful for synthesis. Okay? All right, so that's the end of radical halogenation. Are there any questions? All right, so we'll talk more about, we'll do an example of how to use this to predict the products. But let me talk really briefly about combustion. Okay. But are there any questions? No? All right. So, combustion. All right, so last time we talked about combustion just for a property of alkanes, but now I'll give you the generic equation which is used to determine the coefficients, okay? But when you're balancing a combustion reaction, you're better off trying to balance it the old-fashioned way, okay? But I just wanted to give you this information because this is how it works. So CnH2n plus 2. All right, and then we have the number of oxygens is given by 3n plus 1 O2. All right. So if you didn't want to, so if you had the value of n, which is the number of carbons, you could figure out the coefficients for oxygen as well. So 2n here, CO2, all right, plus 2n plus 2 H2O, like that, okay? So that is the equation you can figure out the balanced combustion. But here, for our purposes, just know the products. Like, say what the major products of the reaction are. For example, in any combustion, right? It's CO2 and water. CO2 and water here, okay? So we'll introduce equations like this for alkanes, cycloalkanes, combustion, just to get an idea of how we can write the formulas, okay? All right, so that was combustion. All right, now to wrap up this chapter, let's do an exercise. So this will be a long exercise, okay? How do we determine the organic products of radical halogenation? And how do we calculate the yields of each? We could do that with the rates we just determined. So how many organic products do you expect for this reaction? All right, that's not the end of it. Estimate their yields. So if you know the relative rates, you can actually determine, and you know the number of hydrogens, you can determine the yield based off the total number of hydrogens and the number of hydrogens that can react to give you that product, okay? So let's take our alkane here, boom, boom. All right. So I gave this example because there are a lot of products and it's a good exercise for this, okay? So, all right. So let's look at this molecule. We're going to name it first. So 1, 2, 3, 4, 5, 6, 7. That's a heptane. All right. Preparation for exam here. How would I name that? There's a heptane. I gave you heptane. So how would I finish writing the name? All right. Good. All right, good. Okay. Now we have to, in order to answer this question, we have to label some of these hydrogens, okay? So right here, we have 2 methyl groups, and if I replace both of them with chlorine, I'll get the same product because they're attached to the same carbon atom, okay? So A, that's HA. I'm going to have HB right here. And then I'm going to start naming this letter D. Whoops, what happened? D. And then this one is G. This one coming out here, that's going to be my HC, okay? So I lettered these based off the kind of carbon the hydrogen is attached to. So I already got G, so this is H. All right. So how many products do you see with those letters? How many letters have I written there? you know, keeping each letter as one. So there's A, B, C, D, E, F, G, and H. So how many products is possible there? 8, yes. 8 possible products, okay? Now, would I ever ask you to write all 8 on exam? No, okay? But this is just for practice. And remember, not going to be tested on this exam, okay? I mean, like, the yield part. Okay, so let's start with letter A. What would A look like? So I'm gonna write the products down here, okay? So letter A. I'm going to put the chlorine where that A letter is. Okay, so A would look something like this. Boom, boom. All right, we got the methyl there. Now, one of these is going to bear the chlorine atom because I replaced that hydrogen with chlorine. That's monochlorination, right? All right. So let's do some practice here. Let's name this compound. Okay. Is it still a heptane? Okay, good. All right. So where would I start numbering though this time? Is it still going to go left to right, or is it right to left? Left to right. Okay. So we get 1 chloro. I'll just number this one. So 1, 2, 3, 4, 5, 6, 7. All right. So I'll just number this example, and then the rest we'll just name it. Okay. So 1 chloro, 2, 4 dimethyl heptane. Okay. All right. So I'm not going to write the yield yet for this because I have to kind of explain. But first, I'll write how many hydrogens are available here to get this product. 1, 2, 3, or 6. So let's look at our original molecule, right? There's 2 sets of hydrogens for A. So how many hydrogens is that? 6. So the rate here is going to be 6 times, all right. Do you remember the ratio for primary hydrogens for monochlorination? It's 1 to 4 to 5. So we're going to put 1 there. 6 times 1. Okay. Now we're going to come back to this later, and then we'll calculate the yields. Okay. So now let's go to letter B. All right. So I kind of have to draw all these first in order to demonstrate what I'm trying to say. All right. So letter B here, instead of see where HB is, I'm going to replace that now with a chlorine. So now let's draw that. So we're going to get boom, boom, Cl. All right, that's B. All right, so let's name this one. Letter B here is, all right, now instead of 1 chloro, 2 chloro, 2 chloro, 2, 4 dimethyl. All right, sorry, I had to put it down here, heptane. All right. So what position is that? So is that hydrogen on a primary carbon, secondary carbon, or tertiary carbon? Tertiary, good. So how many of these type of hydrogens do we have in our molecule? 1. I'm not saying tertiary, just this position. How many HBs did I write up there? 1, right? So that's going to be 5 times 1. Okay. Do I want to write that way? That's all right. So 5 and 6 are the rates. Okay. Sorry, no, actually, no. Let's not write that way. Okay, my bad. Erase that. All right, so I have 1 hydrogen, and the relative rate for tertiary is 5. So I'm going to put 5 there. Sorry, I had it there the first time. So this here is the number of hydrogens. So that's going to be the number of H's times the relative rate, which is this guy. Okay, so that's the relative rate. And 6 is the number of hydrogens that can react. All right? Okay, so let's go to letter C. All right. So how many C's do I got? 1. Okay, so let's draw the product for C. That. All right. All right, haven't already? Go ahead and try to name it. Let's see here. It looks like the number is will the numbering change? Yes. So coral is at what position now? I don't think it's 3, is it? 4. That's all right. We're almost there. 4 coral. Dimethyl. Heptane. And C, again, only one of them, and it's tertiary, so that's times 5. Okay? Let me give you a little, let's just recall this. So tertiary, secondary, and then primary. The relative rates, 5 to 4 to 1. You don't have to memorize these numbers, because I will provide them to you. Okay? You don't have to remember them. All right. Now let's go to position letter D. All right. So D there. So now we've taken care of some of the methyls and then all of the tertiary positions. Okay. Now we're moving to the CH2 positions. All right. Let's start with letter D. All right. So letter D here. We're going to put a chlorine on this position right there. All right. So go ahead and draw it, and then if you can, proceed to name the product. Like here, Cl. Okay. So what position is chlorine at this time? What number? 3. Good. Oh, sorry. Guys, give yourselves a little space here. It's all right. If you don't have space, that's fine. We could just fix that later. My bad. 3 chloro, and then what about the methyls? Are they still the same numbering? Same numbers there? Yeah. Okay. Thank you. All right. So let's look at our little handy chart here. So what position was that? Secondary, primary, or tertiary carbon? Secondary, good. So our rate is 4, but how many hydrogens are available there? 2, good. So it's 2 times 4. Okay? All right. So we could put equal signs here just so it doesn't bother you. 5. And then 5. And then 8. This one's going to be 8. I don't want to solve. Okay. All right, that's letter D. Now let's go to position E. And where was E on our chart here? Okay, that one is on the other side of the central methyl group. So let's draw that. All right, so E. So these are all different products, as we'll see, because the names are all different. So that's how you can tell you drew a different structure. All right, Cl right there. Okay. So the names we drew so far, they all look different. So 1-chloro, 3-chloro, 4-chloro, 2,4-dimethyl. All right, but now here we get a different name, I would think. So where is the chloro at this position? Yep, you're right, 5. 2,4-dimethyl heptane. And since this position is also a CH2 group, it's going to have the same relative reactivity here as D. So 2 times 4 is 8. So for chlorination, the product distribution gets a lot more complicated when you have a lot of different hydrogens, okay? So as you can see here, if you get 8 different products, that's like a nightmarish scenario in terms of trying to get them pure. So you don't want to really do that. If this is the case, we'll try to turn this into like gasoline or something, or I don't know, some kind of fuel, some kind of like oil or solvent, maybe mixture of solvents. Okay. All right. So our next letter here is what? F? Yeah. All right. Okay. All right. And letter F here, that's the last CH2 group on the right. So let's draw that product. Okay. Let's see. Boom, boom, boom. All right, so this time it's going to be on the very end, almost at the very end here. And we get this group right there. All right, so here is where I think the numbering scheme will switch. So where is chlorine at this time? 2. And that would make the methyl start where? Is it still, or the methyl still 2 and 4? Yeah, now it's going to be 4 and 6. And that's because chlorine, if we look at one end, methyl's at 2. At the other end, we switch the numbering. Chlorine's at 2. So we have to use the alphabet to decide which way to number our compound. Good. So we're going to get now 2-chloro, 4,6-dimethyl heptane. All right, so what's the relative reactivity for F? Well, it's still a CH2 group, so it's the same as before. So 2 times 4 equals 8. All right, almost done, okay? 2 more. Letter G. All right, G, however, is so G and H are the 2 last methyl groups we saw. Okay, so G in this case is going to be that central one right there. So let's draw that. All right, for G, we got this guy. All right, so draw the heptane, and this is where the chlorine now will attach. All right, okay, so so what's the longest chain? Is it still a heptane? Do we have to name it complex here? Probably do. All right. What's the parent chain? What's the parent chain? Still heptane. All right. Now, is chlorine part of the main chain or nah? No. So we have to name it IUPAC. We don't have a clear way to name it, a common way to name it. All right. So if your branch is substituent like that, there's a chlorine come off of it, or just a other halogen or oxygen, you don't have to specify the number because there's only one carbon atom. Okay, it's automatically 1. So we would call this what? Yes. So it's just chloromethyl, right? And there's only one carbon, chloromethyl. Very good. All right. So that one's going to come first because the methyl group starts with an M. So 4 parentheses chloromethyl. 2-methyl heptane. Like that, okay? Now let's look at the rate. So this is a primary. Was this a primary hydrogen coming off the Cl? Was that primary carbon, secondary hydrogen, or tertiary? Primary, good. So in this case, G here, we're going to have, and there's 3 possible hydrogens, right? So 3 times 1. Like we saw over here a little bit. All right, so that's going to be 3. Good. Now the last one, H. All right, H is where we saw it was coming off. It's the end of the heptane on the right. Okay, so H there. We would draw something like this. Chlorine comes off at the last carbon, right there. Okay, and I'm missing a methyl group here. Boom. 1, 2, or do I have too many carbons? 1, 2, 3, 4, 5, 6, 7. Nope. Right here. All right. So let's name that one. All right. What would the name be for this one?
1, 4, 6, dimethylheptane.
You got it. Thank you. 4, 6, right? Dimethyl heptane. All right, what's the relative rate here? So that chlorine had how many hydrogens before we attached it? 3. So it's still primary, right? So the relative rate is 1. 3 times 1 equals 3. Okay. Now we are ready to figure out exactly the percent yield of each. Okay? So, Captain, got a question?
H and D because of constitutional isomerism. Sorry, H and A.
H and A? Yes, and that's because
Even though they have different names.
yeah, they have different names. Yeah, they would. They would because the chlorine is further from the methyls in one case. If you look at H, chlorine is at the very end, and then chlorine's like closer to one of the methyls. Yeah, they're still. Good question, because for a second I thought, oh yeah, maybe they are the same, but no. So they are still considered constitutional isomers. Yes. All right, so I want to make a few notes about some of these numbers that I put up here, okay? So, number, all right, of original hydrogens times the relative rate, slash reactivity. Okay, that's equal to H times R. And that's what I did up here. That's H times R. Okay, that's our rate. So our absolute rate for each of these products being formed is the total number. Okay, so that's what we got there. All right. Now, in order to figure out the yield of each product, there's 8, right? 8 products. We have to know the sum of these H times R values, okay? So now we're going to put the sum here. All right. Number of original H's times relative reactivity. All right. So let's add up all these numbers. 3, 6, 22, 30, 40. All right, what is it? 46. All right, so you kind of see here that if we get the numbers wrong, we will get the whole percentage yields wrong. But don't worry, if something we're asking here, if anything, I'll only ask you to draw 3 products and predict the yields of each, okay? Not 8, that's way too long, all right? So now let's figure out the percent yields, okay? So letter A, we have a total of 6 hydrogens over a total, sorry, not 6 hydrogens, 6, that's the rate, okay? And the total sum of that is 46 times 100. All right, so the yield of this product is only 13%. All right, so you're going to take the H times relative rate ratio and divide it by the sum of all those ratios we just determined, okay? So A is 13%. Now let's do B. The only difference here is you just have the different starting value, 46 times 100. So B here is 10.9%. So you notice here that we have 8 of these structures, and if they all add up to 100%, I don't think any one of them is going to be that much greater than the other. Okay, so this is where coordination kind of fails. If you were only wanting one product, so for a synthesis perspective, this is atrocious. Okay, but if you're trying to make like, you know, a solvent, a mixture of solvents for like other purposes, it might have been okay. All right, how about C? What do we get for C? I think the same thing, right? 46 times 100, 10.9%. Now we go to letter D here. 8 out of 46 times 100. That's 17.4, so that's the highest so far. So that's probably our major, I don't know if you consider that a major product, but it might be. Because this one is also 8 out of 46 times 100, 17.4%. All right, we get the letter F. F is also 8 out of 46. 17.4%. All right, and then the last ones here, G and F, which have 3 out of 46. Sorry, G and H. Did I say G and F? 6.5%. No. All right, that's the percent yield for all these products. And if you add the percentages, they do give you 100%. Okay? So we could kind of summarize here. The primary ones have the lowest percentage. The secondary ones, they had the highest yield, okay? But it's only 17.4%. So you got to think for coordination, the number of hydrogens and the relative rate are both important. Because look at here, we had 8 products, right? But each of those are only 2 out of the 4, however many hydrogens there are here, okay? And so they're not a big percentage of your product. They're only 17.4%. So you got a very wide distribution here of products, a big mixture. So not snagly useful for this type of reaction, for coordination, okay? All right, so that's kind of the extent of how we'll that what you can expect for this type of reaction. There are going to be some math involved. Okay. But most likely, what I would ask you is predict, draw all the possible products and pick the major one. If I were to ask this one, ask about this, okay? But for today, just worry about drawing all possible coordination products for a small alkane, okay? All right, are there any questions on that? No? All right, let's take a little break, all right? 10-minute break, and then we'll start discussing cycloalkanes. You may have heard of chair structures. We'll talk a little bit more about that in chapter 4. Yeah, what's up?
Out of the ones of the example, which one would you say is the major product? Then, even though, because like there's 3 of the second.
Yeah.
So like all 3 of those would be the major product.
Yeah, they would contribute most of the mixture for sure. Yeah.
Okay.
But this one, there's like 8 products. You usually don't assign a major and minor because there's just too many.
Okay.
Yeah, major and minor would be like 2 or 3 at the most. Yeah. All right, I'll be right back.
There was 1.1 million people for the Oakland.
Yeah, so you're looking at the carbon. What kind of carbon? Primary carbon? Secondary carbon? Yeah.
No, I was saying, well, because they're getting into that.
not like official like wine. You know, I haven't studied that since I have studied that at all.
Yes.
And then I have
Okay.
It was for like the methyl ethyl.
Yeah.
Do you want it in parentheses like this?
It has to be, yes.
It
One
has to
dash,
be?
one dash methyl ethyl.
Okay, because I think we had done it without the parentheses, but that would be wrong, right? It would have to be a parentheses down here.
You know what this looks like?
Yeah, I can show you.
But I'm not sure. Yeah.
But like, they have a bunch of really cute, some are like simple.
Compound A, right?
Yeah.
Yeah. So you have to do 6 in dash parentheses, 1 methyl ethyl.
Okay.
Yeah.
Because it would be at one, there would be the 2 carbons for ethyl, and then the 1 carbon for
Yeah,
methyl. That's
right.
why. Okay.
Yeah.
And it's almost more stable.
So they're pretty comfy, and I think they're like easy to clean.
Oh, that's nice. Design, pretty, I've never seen anything like that.
Really nice, and it's like a small business, so like when you purchase it, it's like, they donate, I think there was like a thing that they gave me, because you also, when you purchase or not, you get free stuff. But they also have a thing where it's like, oh, like, if you order more than a certain amount, they donate money to like a charity to like, or like fundraiser to like other small businesses.
So my way of thinking it, like, it's gonna be on
I like that.
the market. What do you think is actually, so like at one, there's a ethyl, and then on the other. Is that what you're saying? Like, this is a new chain, basically. So market one, and then at one, there's a ethyl, 1, 2, Andrew.
Hi. What's up?
So this is basically what we were doing right now. It's
Yes.
just from last semester. But
The common name is that like.
so when you're doing the relative yield, like
Yeah.
the numbers that you're multiplying right here come
Yes.
from right here, right? And
Yes.
they don't change.
Right? They never change for any. They're always true for all octanes. Yeah. You're welcome.
So like, yes, like I'm not gonna have. Three, what's the other? It's total, and that's why it's called isopropyl, because apparently why it looks like two, but when you look at it, it's three, because it's and that's the same with two methyl propyl. It's like two, 1, 3, 4. That's the primary. So it looks like 4, but really the chemistry is 3. What do you think of my shoes? Remember?
Huh? Oh. Mine's fancy. Yeah. Cute.
These Converse type shoes. But
Oh yeah. So more comfy? Yeah, for sure. Converse.
Because I have some Converse.
Yeah. Yeah, it's true. They break pretty easily.
If there's a branch that is close to
I have one that, but the common name is isopropyl. It's like when you look at it.
and the common.
Yeah, I used to.
Iso,
Doesn't matter what it is.
What if it,
Because isopropyl, because when you look at it, it looks like a triangle. But when you're considering
All these should be 60.
so it's like the real name is like 1. It looks like 2. Even though it looks like 3, because it's connected to a connection, it's actually just like 2. But really it's like 3. And the same with isobutyl, it's like
No.
See that?
is that isobutyl is because if you look at this by itself, it looks like a connection. It's like 4. But because it's connected to the other molecule, it's really a 3 change. So that's why it's like, or the half, yeah.
So it's 4 instead of 3.
Yeah, so it's isobutyl, but the other half is
I think we do this one. We can start here. So we're doing 3 wrong, and 4.
So it's like what it looks like, the number.
Enough for.
Yeah, okay. And then when it has like more complicated ones, like set-butyl and isobutyl, set-butyl is one one methylpropyl, so it looks this, but then isobutyl looks because it's at isobutyl because it's at blue methylpropyl. Set-butyl is at one methylpropyl. This is propyl. It looks like it has it's like every isochromatin molecule it looks like almost like X.
You want to be the small
Chart will always have it.
What if it's like
Sorry,
super it is, but from the beginning, like hexing, that's what
yeah, so sector is like this. So you do them all through here. And you
Oh,
have
like
this
one
is
side
already
is close.
done.
So like if it was here, you would start here.
It looks like this because it'll be, this is like one that looks like, there's 1, 2, 3, 10, 2, little branch coming up. But then Turkey just looks like next because it's everything has to do them off of here and then branching off of it. And then
Is that page 65 for full set?
so it looks like a
Only
little
like.
X.
Nice.
Circling it outside.
I'm back. Yeah, I'm not back. All right. Let's wrap up this lecture here with our foray into cycloalkanes. Okay? All right. So, guys, just realized this is a new section, so a new chapter here. All right. Once we kind of conquered the next two chapters here, we will know how to draw organic structures pretty well. Okay? So, cycloalkanes. I think we talked about it a little bit, but let's just recap. Nomenclature. So cycloalkanes, they're considered oxidized forms of alkanes because you removed 2 hydrogen atoms, okay? So cyclopropane, so let's just recap here, just to refamiliarize ourselves. Cyclopropane, the box, cyclobutane, the pentagram, cyclopentane, the 6-membered hexagon, and then 7, don't worry about 7, 8 is the stop sign or the octagon, cyclooctane. So I mentioned cyclooctane because cyclooctane is actually, we can actually perform like, we call it biomimetic reactions outside of the living things. So cyclooctane is pretty important in that regard, okay? But anyways, let's go over nomenclature for simple substituted cyclooctanes. Then we'll work our way down until what we saw. And previously, we saw we could do cis-trans isomerism with them, right? So, monosubstituted alkanes here. Oops. So for rings, if you only have one substituent, you actually don't have to specify where it is because they are always given the one position. All right, bromine, methyl. All right, so remember how we named these, right? It doesn't matter what the size is. The cycloalkane is always the parent name, all right? So I'm going to point to this is always the parent name. Okay, so if we look at the substituent though, it's just one substituent, but it's not simple, it's complex, so we have to reread that here. So it starts out right here, 1, 2, 3, 4, and 5. So this whole substituent is complex, so we're going to put parentheses around it and then write the name as if it were a straight alkane. So this would be 4-bromo. All right, 3-methyl. All right, and then what's the, all right, well, how long is that chain though? 5. So what should we put at the end? Pentyl, yeah. Pentyl. Cyclopropane. All right, good. So are there any questions how we named that one, the complex chain there? Any questions?
Verifying that you start numbering closest to the cyclic.
Yes, right. Because remember, this line is just a substituent here. So this line is just where it connects. And this position is at the 1 position. So we didn't put a number in front because it's just 1.
I just want to make sure it's from there instead of from the other end.
Yeah. Right. But remember, this is connecting off the cyclopropane, so we number it that way, yeah. So it's reversed, yes.
Can you review why it's pentyl, not pentane?
Right, so remember, the parent name is not the alkyl chain, it's the ring, so cyclopropane. So this line, this group right here, right, this group right here, that is just a substituent. So that's why it's pentyl. That's part of the substituent name. Yeah. Good. All right. Any other questions about that? No? All right. So now let's go to the polysubstituted. Boom. Poly. Cycloalkanes. All right. Nope, not what I wanted. All right, don't have no stereochemistry on here. Doesn't matter for now. Okay, how will we number this chain here? So you have a few options. You want to number in a way, circle in a circular fashion, right? Where all the substituents have the lowest number. So which one should get the 1? The chlorine? No. We might think it's chlorine though, right? But if we do that, then we have 1, 3, and 5. Where if we numbered from the methyl, we could get 1, 2, and 5. We don't want that. What about if we start from the ethyl? What do we get? Yeah, 1, 2, and 4. So that's better. So that's the way we're gonna go. 1, 2, and 4. All right. So first we alphabetical, 4 chloro, 1 ethyl, 2 methyl. All right, and what size ring is that? Cyclohexane. So don't forget the cyclo, okay? It's technically wrong if it doesn't have that. All right, are any questions how we got the numbers there? Okay. Now let's talk about cis and trans. All right, we have cis and whatever. Cis and trans isomers in cycloalkanes. So in lab we saw cis and trans with alkenes, right? But now in a ring, you can't necessarily rotate the bonds just like we saw in alkenes, right? So we'll have cis and trans isomers. There's no cis and trans isomers in alkanes, linear alkanes, because you could just rotate them around and then bring them to the same side, okay? All right, so I'm going to draw this molecule in 3 different forms. They all correspond to the trans isomer, okay? So I'm going to draw this molecule in 3 different ways. All right, this methyl group is sticking up. And this OCH3, this methoxy group, is sticking down here. Okay, so that is trans. There's also a few other ways we can represent trans isomers. Instead of drawing something up and down, we can have one that is dashed and one that is wedged. So that is also trans. Now, it doesn't matter if you put the wedge on the OCH3 or you put it on the methyl group. So I could also write this, this compound like this. Boom, 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 boom. Like that. Okay. So this whole thing right here, all of these is the molecule. Trans, 1-methoxy, 3-methyl, cyclopentane. All right. Why do we put one with methoxy instead of methyl? Any ideas? Yeah, because the oxygen, right? So compare the names, right? Meth O, meth Y. So oxy would come first. That's the point of first difference for the alphabet. There you go. So these are all trans. So you can draw up and down, do one wedge and one dash, and it doesn't matter where the substituents are. You could do either wedge on one, dash on the other, or flip them, same compound. Yeah, Catherine, question?
Cis and trans on the same molecule?
No, I don't think we could call it that. Yeah.
Even though you can give like 2 wedges and 2 dashes.
Right. Yeah. So cis and trans, usually you need there has to be like only 2 substituents on 2 different carbon atoms, and we're looking at that relationship. Yeah. All right. Any other questions? Trans? Nope. All right. Let's go to cis. All right, cis is kind of the same thing. So instead of drawing it on opposite sides, you would draw it on the same side. So I'm going to say this is pointing down, and this is pointing down. Okay, and then we have you could do it both wedged or both what? Dashed. Good. All right, so the only difference between this molecule and the one on the top is what? What changes in the name? Yeah, you're just going to put cis in front, okay? So I won't ask any stereo. This is what we call stereochem. I won't ask any of this until the second exam, so don't worry about this yet. All right, but we already seen it before, so like in lab, so it should be familiar, okay? All right, are there any questions on those notations? So these are stereoisomers because the arrangement of the substituents now, they differ in space, not necessarily by connectivity. Okay. Now, remember, I don't know if we remember, but when I was talking about alkanes, we talked about what if there's more than 2 substituents? Can we use cis and trans? Yes, if some requirements are met. Okay, so let's talk about a few more. 2 more examples. So, if you have 3 different substituents on your parent chain here, all right, so there's 3 different substituents on 3 different carbon atoms. You can't do that. Okay, so 3 substituents here. So no cis or trans label. All right, because it'd be like, which one are you referring to? One could be cis, one could be trans, right? So you can't have that, both of them in the same name. Okay, so the only way we could name this is just without the label. All right, so how will we number the substituents in this example? All right, coral should have what number? 1. Like that. So now, alphabetical order. 2 bromo, 1 chloro, 3 ethyl, cyclohexane. Good. All right. Now let's look at this next example. This is that exception or requirement I was talking about. All right. So we have 2 chlorine atoms here. All right. So these 2 chlorine atoms, they may look like they're cis and trans, but they're on the same carbon atom. Cis and trans, they have to be like 1 carbon adjacent to each other. Okay. So now let's draw the bromine here, wedged, and then we're going to draw the ethyl group here. All right, so again, 1, 2, and 3, like before. But look at here, both of these substituents are on the same carbon, okay? So substituents are on same carbon atom. Okay, so what we're comparing is these 2. So you want to compare these 2 groups. All right? So it's like saying, oh, what if those chlorines were just hydrogens? It's like that. Since they're the same, you can ignore them. All right? Because they're on the same carbon atom, even though there's 3 different substituents there. Okay? So we're looking at bromine and ethyl, the ethyl group there. So what's their relationship? Cis or trans? Yep, you got trans. So we got trans 2-bromo. 1,1-dichloro. 3-ethyl cyclohexane. All right. So that's as complicated it'll get for naming cycloalkanes. Are there any questions? No? All right. So we'll talk a little bit about the reactivity of cycloalkanes, and I'll mention and start talking about the stabilities of each of them, and then we'll work our way to drawing these structures in 3D. Okay, so let's start with the relative stability of cycloalkanes. Okay. All right. So one way to test the stability of cycloalkanes is to test their heat of combustion. Okay. So the more energy you can release, typically, the more reactive you are, the more unstable you are. But in terms of like relative stability, we're going to look at something called strain in cycloalkanes. But first, let's just review heats of combustion. All right. So heats of combustion. All right, this is a method or way to measure the stability of cycloalkanes. All right. So the formula is very similar to the one we had for alkanes. It's just Cn, but now it's H2n, not 2n plus 2. Okay, for a cycloalkane, plus 3NO2, then 2N CO2, plus 2N H2O. So very similar, except we're just missing the plus 2 for the alkane and then for the amount of water that's produced. Okay? All right. So we can measure these by comparing the chain lengths of propane, butane, and then pentane. All right, so we're going to compare delta H. So this is our combustion enthalpy, so kcal per mole. And then we're going to say the change, we're going to calculate the change in delta H. All right, so propane, this number is negative 530.6. Butane, negative 687.4. And then negative 845.2 for pentane. All right, so let's calculate the change from propane and butane, and then butane to propane. And we'll see the difference between 3 and 4 carbons, 156.8. And then from 4 carbons to 5 carbons, that change is very similar, negative 157.8. But if you take the difference between propane and butane, what's the only difference between them? What additional group is between them? In terms of their structure. CH2, good. So we can actually calculate how much energy is given off for each CH2 added. Okay? So that's what these two values are for the change. So if we take the average of that, we can find that the average energy release per CH2 in a molecule is around negative 157 kcals. So we'll take the average heat of combustion per CH2. So we took those two values and found the average. It's going to be right in the middle, 157.4. So this value is going to be important in our discussions. Okay, so just remember that value. Okay, now I'm going to apply this to cyclic alkanes. This value to cyclic alkanes. Okay, so here I'm going to make a chart. So I'm going to put a line through this. Now we're going to make a chart. Ring size. All right, so here's my delta H of combustion. But this is going to be calculated. Okay, and here's my delta H of combustion. Here is my experimental value, okay? All right, and these values here are still kcals per mole. So let me just write that. Kcal per mole. Kcal per mole.
Professor Andrew,
Yes.
is that just in above there at the negative 157.8?
Yes.
Is there a reason you only have 2 values there?
Yeah, because I'm taking the change from 3 carbons to 4, and then I'm comparing the change from 4 carbons to 5. Do you remember? Oh, so it's like this. So this 2, let me just do this. This 2 is pointing to this value, and then this 2 is for this value.
Thank you.
Yeah.
That's more clear.
Thank you. Oh, yeah. Of course. Okay. So we're just want to make sure that, okay, the change in energy, they should be around, approximately the same because the difference is only one additional CH2 group. Okay. So that's why we didn't compare 1 and 3, or the first and third entry, because that's 2 CH2 groups. Yeah. Good. All right. So we'll kind of see here that our calculated value and what we found in the experiment is it may be the same or it may not be the same. So if the only factor here is CH2 group inclusion and no other factor, no strain, no balancing force, or no net benefit, then they should match. Okay? But often what you see in experiment and calculation, they don't always match up. okay? Because there's something we didn't consider. So there's something called total strain. Okay? And then this is also kcal per mole. And then we could write strain per CH2 group. Okay? Also kcal per mole. All right. So let's start with ring size 3, cyclopropane. Your calculated value here is negative 472.2. All right? But in experiment, it releases actually a lot more energy. So it's negative 499.8. That is, so we could say here the difference is equal to the strain, or, you know, the kind of forces that make this molecule release more energy, okay? 27.6, so that's a lot. So the ECH2 group is strained by 9.2 kcals per mole. So I took the value of the strain and divided it by the number of CH2 groups, 3. That's why it's 27.6, okay? Now, ring size for 4 cyclobutanes, it's not as bad as cyclopropane, but not that great either. 0.9. All right, the strain is less, but slightly so, 26.3. And then each group here is 6.6. They have that much strain, all right? Then we move down to 5, 6, and then we could actually go up to 14, but I'm going to just go 5, 6, and 8, okay? Because those are the most common ones we'll see. So 5, negative 787.0. Okay, so the difference here is lower, negative 793.5. Only 6.5 kcals of strain here. So only 1.3 strain per CH2. So as the ring size increases, it seems like the strain in the molecule decreases because the ring has more flexibility now. Okay, but that the ring's large enough, that flexibility can actually can kind of affect you in a negative way too. So we'll see that with 8. All right, so 6, the prime example of no strain, 944 calculated, and almost the exact same value from experiment. So that's a great result there. 0.1 total strain, so on average 0.0 per group. Okay, because it's 0.1, that's basically nothing. All right. Now let's go to 8. So we say, okay, if it's 6, that should be 0. If we go higher than 6, maybe that would be even better, or, you know, as almost as good. So 8 here, negative 12, 59.2, negative 12, 69.2. So there's some other factors that are now increasing the strain for larger rings, okay? And we'll talk about these results next time, all right? Okay, so what is strain? Strain is some, remember, steric hindrance, torsional strain. Torsional strain is usually one of the things responsible for strain. The other one is bond angle strain, which we'll talk about next time for cyclopropane. All right, that'll be it for today. I'll see you in 801.